Welcome to RTL Audio Lab. This is Isaac, and in this video we will go over the SPI controller logic that configures the audio codec in our SPI audio processor design. The SPI controller is the third out of the four major components in our SPI audio processor design's top level, as mentioned in previous videos. The SPI controller logic is partitioned into two submodules, the SPI Master and the SPI Driver. Let's start with the Master. The SPI Master is a generic module that implements the master device in a single slave SPI bus. In addition to the standard SPI signals, the clock phase and polarity of the SPI Master can be changed at runtime using the corresponding input ports. The bit width of a transaction can be adjusted during the module instantiation. Just as a heads up, even though configuration options for the clock phase, clock polarity, and transaction bit width have been added to the RTL description, most of them have not been thoroughly tested. The only hardware validation has been done by communicating with the audio codec on the set board with its default settings and at a fairly low speed. Because we only use this interface once after powering up the system, this is not a problem. Here we can see the RTL description of the SPI Master module. You can pause the video at any time to look at it in more detail. My original goal when writing the SPI Master was to have a module that supported all modes of the SPI protocol. As I shifted my focus to the audio processing elements of the design, this universal support lost relevance. This is to say, if our only goal is to configure the audio codec, a single mode SPI Master can be implemented with a much more compact RTL description. I just happen to have this version ready to go, and it works the way we need it to in this context, so we might as well use it. The SPI Master is a generic module that could, in theory, be used to interact with any device that supports SPI slave communication. Thus, we need to feed it the data that we want to send to the SPI slave device, in our case, the audio codec on the set board. This is the job of the SPI Driver module. To understand how the SPI Driver feeds data to the SPI Master, we need to be aware of the following. The audio codec defaults to I2C communication after each power cycle. To switch to SPI mode, the chip select signal must be pulled down 3 times with dummy transactions following power up. After that, the codec will remain in SPI mode until the next power cycle. Except for the PLL register, each read and write operation includes 4 bytes. The least significant bit of the first byte determines whether the SPI Master wants to do a read or a write operation. The second and third bytes indicate the 16-bit address of the register that the SPI Master wants to access. The fourth byte contains the data sent by the master in a write operation or returned by the codec in a read operation. And finally, all registers in the audio codec contain 1 byte, except for the PLL register, which contains 6 bytes. The audio codec on the set board is a highly configurable device, with built-in mixing and processing capabilities. Of course, since we would like to do all the processing ourselves in the FPGA fabric, the only thing we need the codec to handle is the D2A and A to D conversion. So our setup should look like this. This simple configuration requires quite a few SPI transactions to set everything up. These are captured in the main FSM within the SPI driver, and as you can see, there are a lot of register values to set. As a guide, I used a reference project by Digilent where they performed the SPI configuration in software, but of course, we do everything in hardware in this module. The SPI controller includes an enable input, which is used to trigger the codec configuration by pressing on the set board's button. This must only be done after power cycling the board. If the sync is reprogrammed with the power on after the codec has been configured, audio data will start flowing as soon as the bitstream is programmed. Okay, so now we have covered the 3 major supporting elements of our SPI audio processor's top level: the debouncer, the master clock generator, and the SPI controller. On the next video, we will turn our attention to the audio processor core, which is by far the most interesting element in our system, and where we will spend most of our time. Thanks for watching. See you then.